Okay, so in this video, we're going to be titrating a weak base with a strong acid. And what's really interesting here is that they give us the weak base of CH3-2NH. And if you take a look at that, it looks kind of like an acid with an H on the end. But I want you to be careful because dimethylamine, anytime you have an amine, it's going to be a base. But then on top of that, we're titrating it with HClO4. And remember that every single time that we titrate, it has to be done with a strong acid. Also, remember, every time we do a titration, the number one thing that we're going to do is do the stoic. That means that we are going to take care of the big dog, which is either a strong acid or a strong base, and it's going to be done in millimoles or moles. Number two, what we're going to do is we're going to, let's keep that in there, is do the equilibrium. Now, what that means is that after we've taken care of the strong acid or strong base that we're titrating, we're going to see what's left over, and then we're going to do something with it. So let's take a look at this problem a little bit up close. And the number one thing you need to do in all these problems is you need to write a formula for what it's doing. So here we have our base, and normally what we do if we just had our base is we throw it into water and we'd see what happens in an equilibrium. But remember, whenever we're titrating, first we have to take care of the big dog or the acid. Now, when I look at this, the acid always is going to be written, it's always going to be a strong acid. So instead of writing it as HClO4, we know that the only thing we really care about here is the H+. And then over here, we have a base. And so we know that a base and an acid will react to neutralize each other. So if I were to write this out, I'm going to take my CH3, parentheses 2, NH, which I know is a base because I'm reacting with a strong acid. This, again, as we said, this H right here can seem a little bit confusing to you, but again, whenever we have something like an amine, we know that it's going to be a base. Just be aware of that. And we're going to react that with the acid. Now, some people would write it in as HClO4 on this side, and on the other side, they would put ClO4 minus, knowing that this and this just cancel out. So if you ever see that, don't be frightened by it. But because we only care about the H plus in the strong acid, we're going to write H plus H plus here, and that's going to form CH3 2 NH2 plus. And it makes sense if you think about it here, because when we just add an H plus to this, which is neutral, it's going to give us two H's, and we're going to have a positive here. So what do we do from there? Well, we need to figure out the millimoles of each of these things. Now, if we do this independently here, I'm going to do this on the side, and I'm going to do this for the dimethylamine. When we start off with that, we have and let's take a look here so we see where we're getting it. We have 0.5600 times the molarity, and we know that molarity times volume equals moles. So when I'm doing this now, I'm going to take my molarity, which is 0.5600 molar, and I'm going to multiply that by my milliliters, which is 156.0 milliliters. And when I do that, I'm going to get millimoles, and we're going to keep it in millimoles here because why bother switching it to something else? So that's going to give us 10.1 millimoles. Now, if we do the exact same thing here for our H+, this is for this. If we do it for our H+, what are we given here? Well, we have 562.9 milliliters, and we have a 0.1800 molar solution. So how do we put that in here? Well, the same thing. We're going to go 0.1800 molar. We're going to multiply that by 562.9 milliliters, and that's going to give us our moles, or our millimoles. And when we do this, we know we're going to end up with, I actually did this. So our job now is to make sure that we have do the problem with stoichiometry, with moles. And the equation we're going to use is we're going to use molarity times volume equals moles. And we're going to do that first for the base, and then we're going to do it for the H plus. So when we do it for the base, we see that we have 156 milliliters and 0.5600 molar. So we're going to put this over here. We're going to go 0.5600 molar times 156.0 milliliters, and that's going to give us our millimoles. And when we do that, we're going to end up with 87.3 millimoles. Then we're going to do the same exact thing for our hydrogen, H plus, molarity times volume equals moles. And we take a look up here, we see that we have 562.9 milliliters and we have 0.1800 molar. So we're going to put that into here, and we're going to write 0.1800 molar times an incredibly large amount of volume, 562.9 milliliters. And when we do that, we're going to end up with 101.322 millimoles. So when we go back to our equation, I like to do an ICF, right? The initial amount here that we have is going to be, and actually I should have given more significant figures. This is 87.3600, and I'm going to keep them in here because that's helpful in our problems until the very end. 87.36 millimoles here, and here we have 101.322 millimoles here. And we have nothing over here on this side to start with. So what we know is that since this is a one-to-one relationship right here, one-to-one, that all of this is going to get used up because there's less of it. 87.36 is this going to be subtracted. We have none of this, and then we're going to subtract 87.36 millimoles of this. And what's really important when you look at that is that when we take a look at the math on this, we're going to end up with approximately, and by approximately I mean exactly, 13.962 millimoles. When we have that number right here, that's pure H plus that is left over after we tried to titrate. So our goal was to titrate this and neutralize it, but we had so much H plus that we completely used up all of this, and we ended up with this amount of millimoles of H plus just sitting there. Now, it is important to realize that we're also adding 87.36 millimoles of our weak acid. But here's what you need to be aware of. This weak acid, if we were to take this millimoles and we were to divide it by its volume and whatnot and figure out our molarity, we could solve for the amount of H plus that's being released by this. But it is nowhere near as much as the pure H plus right here. So this right here, this is going to be the only source of H pluses. So when we have that, all we need to do is make this into molarity, because we love it when we have an excess of a strong acid. We're going to take this whole thing right here, and we're just going to divide it by the two volumes added together. We had 156.0 plus we had 562.9. And when we do that, that's going to give us our molarity, because these are both milliliters, and the milli is going to cancel, and you'll end up with moles per liter. And when we do that, we'll end up with 0.0194213 molar is our molarity. That's the concentration of our H plus. Now, they're wanting us to solve for pH, and we know that pH is always equal to negative log of H plus. So in this case here, it's going to be the negative log of 0.0194213. And again, we're keeping a bunch of numbers in here because we know at the end we're going to cancel, we're going to use the correct significant figures, and we're going to end up with a number of 1.71172. That's our pH. Now, they asked us to solve for to two significant figures. And remember, significant figures, whenever we're dealing with a pH, come after the decimal place. So it's only these two that count. So our final pH in this is going to be 1.71. And if we just take a look back and see whether or not that would have been what we had to do if we were doing on the AP exam. So we have three significant figures here. No, four here, four here, four here. And by three, I mean this also has four. So the reality is our answer should have had four, but because the ALEKS wants us to only have two, we have two. Hopefully this has been helpful to you.